Hi. So we're going to go ahead and start chapter 7 which discusses the central limit theorem. But before we do, I just want to do a little demonstration that may help with um, understanding the whole point of the central limits theorem because essentially we have a lot of sample variability and sometimes we don't take one sample of a population, but we take many samples of a population. And they're doing that right now with like the coronavirus. So they're trying to take a bunch of samples and trying to see some commonalities. Like one of them, they're trying to see if blood type is less likely to be the viruses to be retrieved. Like if you have a certain blood type, then you're less likely to get it. Gender, if you're biologically male or female. So they're taking out of the entire population of the US, they're taking all these other samples, and all these other samples have variability. So the central limit kind of does everything we did in chapter 6, but with many samples. So what does that look like? So if I just went to an Excel spreadsheet and I picked a population of a very small population of odd numbers, let's say I picked 135. So that's my population. Let's just say I picked samples of size 2. So if I picked, let me put it here, samples of size 2 from this population, well, if I wanted to grab one of these two of these numbers, the first possibility could be 1 and 3. What are the other ones? So the second sample would be 1 and 5, right? And what is the third sample? Right? 3 and 5. So essentially I'm just taking sample sizes of 2 from a population of 3 elements, which are 1, 3, and 5. So let's just say these are 3 different, the population itself has its own descriptive statistics. So let's go ahead and just find the average of these. So if I clicked average, I would just highlight the cells and I would get 3 as the average. Well, what would be the average? And then let me put the word average over here so we know. So the average of the population is 3. And so if I wanted to find the average of the first sample, I would do the same thing, right? And I could just drag this over like this and then. So the average of the first sample is 2, and the average of the second sample, 3, is 3, and then the sample 3 has an average of 4. So notice that as I take different samples from the same population, my averages are different. However, I do know that the population average is 3. So there is variability in the mean, right? When you take samples from a population, it does deviate away from the population mean. But the central limit theorem that we're about to discuss says, well, just don't look at each sample's average. Let's take the average of all the averages. So if I took 2, 3, and 4 and found the average between these 3 numbers, what would I get? So I would say the average of the averages. Okay, that would be equal to the average, and I'll double click, of these 3 numbers. Hit enter. Look at that. I know you think I'm crazy, but I'm not crazy. I would never lie to you. Look at that. The average of the averages is the exact average of the population. That means that if I take a bunch of samples, and within the sample, we said in chapter 1 that we have sample variability, and so they're just gonna, all different distributions will have all different statistics, right? And that's why we would like to standardize, right? That's why we have like a z-score to standardize different distributions with different descriptive statistics. The central limit theorem says, well, if you're taking different samples from the same population, if you take the average of the averages, that average should be pretty close to the population average. So that's exactly what we're doing. But of course, a population of 3 doesn't really make sense to us, right? Because if we just look at the census, our population's like millions and millions, right? So these samples could be thousands, but what this helps is if they take, let's say you have a population of 1 million and you take samples of thousands and you take 3 samples of 1,000, at least you know if you took the average of the averages that it would be fairly close to the population average, which means that you wouldn't need to know the population average. You could get a really good idea of what it would be. So let me do another example, a simulation with Reese's Pieces. Okay, so here is a Rossmann Chance applet collection. This link is inside the bottom of our My Open Math class sites. And I think this is a really good example. And it has a little Reese's Pieces machine. It's kind of funny. So let me just say the probability of drawing an orange is 50%. So I don't think it is because I think there's like 3 colors in Reese's Pieces. So I'll put 0.3. And let's say I want to select 25 candies. Maybe that's as much as in a little bag. And let me go ahead and just take one sample. And I'll show the summary statistics on the graph, and we're going to expect normal distribution. Or I guess we don't really need that right now. And so let's go ahead and draw a sample. So it's going to draw one sample of 25 candies. And notice the mean is 6, right? And the standard deviation is really small. What if now, out of the whole population of Reese's Pieces, I took not one sample, but 5, right? Because we took 3 samples of the population on the Excel spreadsheet, right? We had 3 samples. So maybe here, I'll take 5 samples of Reese's Pieces of size 25. So I'm taking 5 samples, and in each of those 5 samples will be 25 Reese's Pieces. And what this applet does is just computes everything for us. So it's drawing all those samples, right? And they're drawing 5. So, and notice that they have a mean of 7. So we got 6 and then 7. So let's go ahead and make it a larger number of samples. Now I'm going to take 15 samples, each size of 25, in which I said 30% was the probability of drawing an orange, right? So let's go ahead and draw the samples. So I made it really quick. So notice the mean didn't change that much, right? It was 7.38. I got 6, then 7. Notice we have a standard deviation of about 2, right? So the average number of orange candies is 7, give or take 2, right? And so now I took 15 samples of 25 each. Right. So let me go ahead and now increase the number of samples. So now let me make the sample 25, all drawing each of size 25 Reese's Pieces. I know I'm making you hungry. Look, did the mean change? Nope, right? Let me make it even bigger. Let's do 75 samples of size 25. And look at the mean. So this average is this average of the averages. And so as I'm increasing, and I'll just do 100 just for, the example's sake. So I'm drawing 100 of samples of 25. So I have 100 samples. So if I went to my Excel spreadsheet, I wouldn't have sample 1, 2, 3. I would have sample 1 through 100 and take each average and take the average of the averages. And that average of the averages is 7.5. So we can get a good idea. And I probably would assume that the average of the population is about 7.5. Okay, so so far, let me go ahead scroll up a little. Down here are sliders. So I went ahead and left the probability the same, and the sample size in our case was 25. If I can get there. There we go. And so that's the mean was 7.5. And we could tell the standard deviation stayed around 2. So I bet you the population standard deviation is about 2 and the average is about 7.5. So, and then if I increase the number of samples, sample size, right? What's happening to the mean and the standard deviation? So now I'm taking samples of 86. I took 221 samples of 86 Reese's Pieces. And you can see that as my sample size get larger, the descriptive statistics change. So the idea is that you want to keep the sample size fixed, right? Like we did. We only kept selecting 25 candies for every sample. And then the only thing we changed are the number of samples. And notice here the mean again, and I took 221 samples. And notice here again, the standard deviation stays around 2 and the average stays around 7, 7.5. So we can assume that the average is about 7 and the standard deviation is about 2 for the population, all Reese's Pieces in the entire world. So you can see that as we take more and more samples, and this is what the central limit theorem says, is as you take more and more samples, the closer you get to the true population mean and standard deviation. Okay, so that is chapter 7. That's exactly what we're doing. All we're doing is taking not one sample and finding descriptive statistics. We're going to take many, many samples and take average of those averages, and then we can estimate a population. So it's all about estimation, right? So if I went to the first page of our chapter, right, let's come back to the notes. This is exactly what we're doing. The central limit theorem states that the shape of the distribution of the sample mean becomes approximately normal as the sample size n increases regardless of the shape of the population. So if I went back to the summary stats, and let's just say I picked a sample size of 5. Notice that the sample size of 5 is skewed right. If I increase this sample size, so I'm not touching the number of samples, I will always have the 221 samples. If I increase the sample size, look what happens to the peak. So I increased it to only 6 and it already is taking the shape even though it's still skewed right. Let me increase it and watch the change. See how the middle is moving? And so let me take a sample, let me take 221 samples of size 50. Oh wait, that didn't. There. So if I take 221 samples, so I have 221 columns, right, of samples, and I increased from 5 to 50, so I changed my sample size to increase. Notice the shape now is not skewed right and now makes a normal distribution shape. So essentially what we want is we want to take a lot of samples, and within a lot of samples we want to take the largest amount of sample size that's reasonable for us. Because remember, in real life, we're doing research, and research costs money and time, and sometimes like in a crisis right now that we have, there's like not a lot of time. So we're just, you have to think in the real world when you start doing research yourself, there's like funding involved. So again, a sample size of 50 and at a Reese's Pieces company where you're taking 221 samples may not be, reasonable for the cost that it would take and the time. Okay, so if I go back to the notes, that's exactly what the central limit theorem says. It says that as you take this sample size to be so large, you will eventually get a normal distribution. That's the central limit theorem. Okay, so now let me go ahead and draw like a picture here. So let's say here's the population. And if I went ahead and drew some samples, so here's a sample, 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 right? So again, if you take the average of this sample, size n, right? This size. So you have all these averages with all these samples, right? And if we took the same sample size and took the average of each sample, right? That if I took the average of these, it would be close to the true population, right? So the average of the averages will take us to the true population average, right? And the central limit theorem just states that we'll take a sample size big enough, right? Increase it, and then your data will become approximately normal. So remember when we took a really small data set? Remember we took a small, like 5, and it was skewed right? And then as the sample size increased, right, we would get this normal distribution. And so that's what this is saying here. It's like you can take the average of the averages of a sample size n, and that will give you a pretty good estimation of the population average and standard deviation. Okay, that's the first thing we get. The second thing we get is as your n increases, so make n as big as possible towards infinity, then the data is normal. So those are two things we get from here, from the central limit theorem. So the next question is, what is large enough? What sample size, Darlene, should I take that's large enough? Well, we have a rule of thumb in statistics, and so this comes from the law of large numbers. And we say, what is large enough, right? Well, large enough depends on the original population, of course. But overall, a good rule of thumb is at least 30, right? Or you should already know that the data comes from a normal distribution. If it tells us that it is already normal, then don't worry about it. If they say, oh, the population's normal, okay, boom, I'm going to go do my thing. If it's not, if they don't tell you that, then you will have to verify that your sample is at least 30, and there's also other verifications that we'll discuss in the future for sure. Because in real life, in real research, it's not told to us, and we have to research that ourselves.